All right, let's get right into it. Welcome to this last-minute revision explainer. I'm your host, and today we are getting intensely focused. If you're a GTU Semester 4 student staring down the barrel of your Plastics Testing-1 exam, subject code 3142311, by the way, you are in exactly the right place. Grab your notebook, grab a pen, and let's clear away all those distractions. I've got my notebook ready to go. We've definitely got a lot of ground to cover today, right? We absolutely do. We're targeting the absolute highest yield topics today, and we're going to move deliberately. The goal here is for you to memorize exactly what you need to write on that exam paper. So here's our agenda. Number 1, melt flow index. Number 2, the spiral flow test. Number 3, the cup flow test. Number 4, the water absorption test. And number 5, the bulk density test. Quick question, why are we just focusing on these 5 tests? Simple math. Together, units 3, 4, and 5 carry a massive 45% of your total exam weightage. That's 15% each. By mastering just these topics today, you are literally securing a huge chunk of your final grade. Let's not waste any time. Starting with Section 1, the Melt Flow Index, or MFI. If you study literally nothing else today, lock your focus in right now. Here is your exact ASTM D1238 exam definition. Write this down. Melt flow index is the weight in grams of molten plastic extruded through a specified die in 10 minutes under prescribed conditions of temperature and load. Okay, so in plain English, it's basically a measure of how easily the plastic flows once it's melted. Exactly. It's a gravimetric flow rate. And here is why this is absolutely crucial in the real world. MFI is an inverse measure of molecular weight. So a high molecular weight plastic is kind of thick, it's more resistant to flow, which means it has a low MFI. On the flip side, a low molecular weight plastic flows super easily, giving you a high MFI. Processors rely on this exact number to set up their injection molding or extrusion machines correctly. Now, you need to be able to draw and label the MFI apparatus from memory. Picture this in your head. At the center, we have a vertically positioned insulated steel cylinder. We call this the heated barrel. Inside that barrel is where your test specimen goes. Right above it sits the piston, and resting directly on top of that piston is your standard weight. Finally, at the very bottom of the barrel, you have the die.
Okay, but in the exam, if they ask for the apparatus details, do I actually need to know the exact dimensions of that die, like the specific numbers?
Oh, you absolutely do. The standard die must have a smooth, straight bore that is exactly 2.0955 millimeters in diameter, and it must be exactly 8.0 millimeters in length. Jot those precise numbers down. They are non-negotiable. Now, these prescribed conditions aren't just arbitrary. They change depending on the plastic you're testing. You must memorize these 2 examples. For polypropylene, or PP, the test is run at 230 degrees Celsius with a 2.16 kilogram load. For high-density polyethylene, or HDP, it's run at a cooler 190 degrees Celsius, but with that exact same 2.16 kilogram load. Writing both of these specific conditions in your exam answer proves to the examiner that you truly understand ASTM D1238. Let's walk through the procedure. Do not rush this, and do not skip any steps. The examiner is looking for all 5. Step 1, clean the apparatus and preheat the cylinder to the specified temperature for your specific material. Step 2, charge the cylinder with a measured quantity of your moisture-free plastic sample. Insert the piston and wait about 4 to 5 minutes. You need it to reach thermal equilibrium. Step 3, place the standard weight on top of the piston so the plastic actually begins extruding through the die. Step 4, this is key. Discard the initial extrudate. You do this because it might contain trapped air bubbles or contaminants. And finally, Step 5, cut the extruded plastic, which we call the extrudate, at fixed time intervals and weigh each cutoff very carefully. Okay, I can definitely visualize that process. But now I have a pile of plastic cutoffs and their weights sitting in front of me. How do we actually calculate the final MFI value from these collected pieces to get our answer?
That is the million-dollar question, and it's exactly where the formula comes into play. Let's look at that.
I want you to write this formula huge on your page. MFI equals the average weight of the extrudate in grams multiplied by 600, all divided by the time interval in seconds. Wait, why are we multiplying by 600? Good question. Remember our definition? MFI is legally reported as grams per 10 minutes. Well, there are 60 seconds in a minute, right? So 10 minutes is exactly 600 seconds. Multiplying your lab result by 600 simply standardizes whatever random time interval you used to that official 10-minute reporting window. Let's ground this with a quick mental math walkthrough so it really clicks. Say we're testing a polypropylene sample. We're making our cuts every 60 seconds. We weigh one of those cutoffs and it comes out to 0.180 grams. Following our formula, MFI equals 0.180 multiplied by 600, and then we divide that by 60. Well, 600 divided by 60 is just 10, and 0.180 multiplied by 10 gives us an MFI of 1.8 grams per 10 minutes. It really is that straightforward. Now, listen to me carefully. Write this down. This has appeared in the GTU exam as a 7-mark question in 7 out of 8 past papers. They're going to ask you to define it, draw the apparatus, explain the significance, list the steps, and write out the formula. If you study one single thing from Unit 5 tonight, it absolutely must be MFI. Okay, moving on to Section 2, the spiral flow test. Hold on a second. MFI is for thermoplastics, the stuff that melts and flows. But what if the plastic is a thermoset compound? We can't just melt that in an MFI machine, right? Wouldn't it just cure and totally block the barrel? Hit the nail on the head. Thermosets cure and harden permanently under heat. You absolutely cannot use an extrusion plastometer for them. For thermosetting molding compounds, we have to measure how they behave under heat and pressure while they're in the process of curing. And that is exactly what the spiral flow test does. This test, which is governed by ASTM D3123, measures 3 combined characteristics at once: fusion under pressure, melt viscosity, and gelation rate. Basically, the material is forced into a spiral channel using a transfer molding press. The longer the plastic manages to flow through the spiral before it finally cures and stops moving, the higher its flow rating. The procedure itself is pretty simple, but you must write out these 4 specific steps for full marks. Step 1, load your preconditioned low-pressure thermosetting compound into the press. Step 2, apply the specified molding temperature and transfer pressure. Step 3, the compound gets forced through a sprue and is allowed to flow along the spiral mold cavity. Step 4, once the curing is fully complete, you open the mold, pop out the hardened part, and literally read the flow length directly from the molded specimen itself. Interpreting the result is a direct inverse relationship. Make absolutely sure this is in your answer. A higher spiral flow length means the material had a lower viscosity and much better flow behavior before it cured. Industry actually classifies compounds based on this exact test. Low plasticity is a length of 1 to 10, medium is 11 to 22, and high plasticity is 23 to 40. Here is your GTU tag. Write this down. This appeared as a 3- and 4-mark question in multiple papers, including the most recent mid-sem paper. It is the perfect, concise process question, so have those steps memorized. Let's look at Section 3, the cup flow test. Often, the exam will try to trick you by asking you to compare the 2 tests for thermosets, so you need to know the exact difference. The spiral flow test measures the flow length using a spiral mold to assess viscosity. The cup flow test, on the other hand, measures flow time and completely cured time using a cup-shaped mold. You take a pre-weighed charge of your material, put it in the mold, apply pressure, and then note exactly how long it takes for the mold to close, meaning the cup has been fully formed, and then how long it takes to fully cure. Write this down, asked alongside spiral flow. Know both together. They love testing them as a pair. All right, we are pivoting to Unit 4, Analytical Tests. Section 4, the Water Absorption Test, governed by ASTM Standard D570. This is absolutely critical because plastics used in humid or wet environments naturally absorb water over time, and this absorbed moisture drastically degrades both their electrical and mechanical properties. Now, the procedure for this is highly specific, and examiners are actively looking for the exact numbers. Step 1, you must dry a disc specimen, and it must be specifically 76.2 millimeters in diameter and 3.2 millimeters thick, in an oven at 50 degrees Celsius to bake out all the existing moisture. Step 2, weigh the dried specimen. This is your initial weight, W1. Step 3, totally immerse that specimen in distilled water at a standard laboratory temperature of 23 degrees Celsius for exactly 24 hours. Step 4, take the specimen out, immediately wipe it dry with a cloth so there's no surface water, and weigh it again. This gives you your final weight, W2. To calculate the total percentage of water absorption, you use this formula, W2 minus W1. Take that result and divide it by W1, and then multiply the whole thing by 100. Let's run a quick example to be safe. So if the dry plastic, W1, weighs exactly 10.00 grams, and then after 24 hours in the water, it weighs 10.05 grams, which is our W2.
Exactly. So W2 minus W1 is just 0.05 grams. Divide that 0.05 by the original 10 grams, and you get 0.005. Multiply by 100, and your water absorption is 0.5%. Easy. Now, you must also list real-world applications where this actually matters to get full marks. Some great examples to write down are electrical cable insulation, where trapped moisture causes dangerous shorts, or things like water pipes and outdoor patio furniture.
Write this down. This appeared in 6 of 9 total papers. It's almost always a 3 or 4 mark question, and it has actually appeared once as a massive 7-mark question. Know the dimensions and know the formula cold. Do not skip this one. And finally, Section 5, the bulk density test, sometimes called apparent density. So is bulk density just the regular density of the plastic, like just basic mass over volume? No. And honestly, that is the #1 mistake students make on this exam. Bulk density is the mass of the plastic per unit volume, including all the air spaces between the granules or powder. It is absolutely not the true solid density of the material. Think of a big glass jar filled with marbles. There's a ton of empty airspace between those marbles, right? Bulk density measures the mass of the marbles plus all that empty airspace. The test uses a super simple graduated measuring cylinder, usually 100 or 500 milliliters, and a weighing balance. Step 1, weigh the empty cylinder. Step 2, pour the plastic granules or powder through a funnel from a standard height into the cylinder. And listen up. Here is the magic phrase you must underline in your answer: without tapping. You cannot tap, shake, or shimmy the cylinder to settle the granules, because doing that artificially reduces the airspace. Step 3, read the volume occupied by the material in the cylinder. Step 4, reweigh the cylinder to find the exact mass of the plastic sample inside. The formula is a breeze. Bulk density equals the mass of the sample divided by the volume occupied. You express this in grams per cubic centimeter or grams per milliliter, but why do we care? Well, out in a factory, plastic granules are fed into massive processing machines through large metal funnels called hoppers. Knowing the bulk density tells the machine operator exactly how much physical weight of plastic will actually fit into that hopper's volume. That is completely crucial for setting up continuous, uninterrupted machine production. Final GTU tag for today, write this down: 7-mark question in 3 NSEM papers, 4-mark in midsem. This faculty loves this test because it proves whether or not you actually understand the practical, everyday industrial handling of raw plastic powder. All right, we have covered exactly what you need. You now have the precise formulas, the critical step-by-step procedures, and the standard lab conditions for 45% of your Plastics Testing 1 exam weightage. Honestly, this feels so much more manageable now. The trick just seems to be getting those very specific numbers and step sequences committed to memory. Absolutely. Industrial testing is all about exact, flawless adherence to standard procedures. There's no room for guessing. So here is your final challenge before you close your notebook today. Without looking back at your notes, can you redraw the MFI apparatus and label the standard die dimensions? Can you accurately outline the spiral flow diagram? Test your recall right now, because getting this right today makes you a much better engineer tomorrow. Thank you so much for joining this explainer session. And seriously, best of luck on your exam. You've got this.